Artemis II proved we can reach the moon. 4 astronauts left Earth orbit for the first time in over half a century, traveled 250,000 miles into deep space, and came home alive. But what that mission didn't prove is whether we can survive what comes next. Because the moment you step off that spacecraft, the problem changes completely. The moon is trying to kill us. Not metaphorically, not in the poetic sense that space is dangerous and the moon is part of space. Literally, specifically, in 4 distinct ways that NASA engineers have documented, named, and are still trying to solve. And in approximately 18 months, we're sending 4 people there anyway. Artemis II proved humans can survive the journey. The crew is home, the mission is marked a success, and every press release from every space agency involved has used the word historic at least twice. All of that is true. What is also true is that the moon's surface is one of the most hostile environments in the solar system, and the list of things we still don't fully understand about surviving on it is longer than most people realize. Start with the dust, because if you ask the engineers and geologists who have spent careers studying the Apollo samples what they're most worried about for a crewed lunar surface mission, dust comes up before almost anything else. Lunar regolith isn't like dust on Earth. On Earth, dust particles get tumbled around by wind and water and contact with other surfaces until their edges round off. The moon has none of that. No wind, no water, no weathering of any kind for billions of years. Lunar dust particles are sharp, jagged at the microscopic level in ways that make them more like powdered glass than anything you'd find on your windowsill. The Apollo astronauts were on the surface for hours, not days. And even in that time, the dust was a problem they hadn't fully anticipated. It clung to everything. Suit fabric, visors, equipment surfaces, the inside of the lunar module. It scratched faceplate coatings. It degraded spacesuit seals. Harrison Schmitt, the only geologist to walk on the moon, developed what he described as lunar hay fever after just 1 EVA. Nasal congestion, sneezing, a sore throat. His body was reacting to dust that had made it inside the habitat module despite every precaution. The symptoms faded after a few hours, but the mechanism was never fully understood, because he was the only one it happened to severely enough to document, and there were only 12 people who ever walked on the surface, which is not a sample size that tells you very much about anything. Artemis III will land at the South Pole. The South Pole is not the equatorial terrain the Apollo missions explored. It is a fundamentally different environment, and some of what makes it scientifically exciting is exactly what makes it dangerous. The permanently shadowed regions near the poles, craters that haven't seen sunlight in billions of years, are where water ice has accumulated over geological time. That ice is the reason we're going back. It is a resource, a potential source of drinking water, and rocket propellant both. It is also the reason the dust problem gets more complicated. Water ice mixed with regolith at cryogenic temperatures creates a surface science that nobody has tested with a crew standing on top of it. The temperature swings at the lunar South Pole are extreme in ways the equatorial landing sites never were. In sunlit areas near the pole, surface temperatures can reach 120 degrees Celsius. Step into a permanently shadowed crater, and it drops to -200 degrees Celsius. Those two environments can be separated by a few hundred meters. A suited astronaut crossing that boundary carries heat from one zone into another. The suit's thermal regulation system, already working hard in the sunlit terrain, encounters a completely different set of demands the moment the lighting changes. Those transitions have been modeled. They have not been walked through by a person. Then there's the radiation, and the Artemis II mission left this question more open than it closed. The crew spent 10 days in deep space during solar maximum and returned safely. The sun was cooperative. It stayed cooperative for the entire mission. The solar particle event that the Orion radiation shelter was designed to protect against never materialized, so we have data on what 10 days in deep space looks like during a quiet sun. We do not have data on what 10 days in deep space looks like when the Sun decides to produce a major coronal mass ejection aimed at the Earth-Moon system. Because that didn't happen, on the surface of the Moon, the calculation changes again. Orion has a reinforced radiation shelter. The habitat modules planned for future surface stays provide some shielding from their structural mass, but a spacesuit provides almost none. And the South Pole surface missions are planned for up to 30 days. A single large solar particle event during an EVA, a crew member outside on the surface, no overhead cover, full exposure to the unfiltered solar wind, represents a radiation scenario that the current mission architecture handles primarily by hoping it doesn't happen during a surface walk and getting the crew inside as quickly as possible if it does. The response time from EVA to full shelter is measured in minutes. In a major event, that could matter enormously. The galactic cosmic ray problem runs underneath all of this and gets the least attention because it has no solution. Galactic cosmic rays are high-energy particles accelerated by supernovae and other cataclysmic events across the galaxy. They travel at nearly the speed of light. They penetrate essentially everything: lead, water, the structural hull of a spacecraft, the rock of a planetary surface. The physics of shielding against galactic cosmic rays is punishing. Adding more material helps at the margins, but never solves it. And cumulative exposure over a 30-day surface mission adds measurably to the lifetime radiation budget of everyone who goes. We know this. We're going anyway. The data from the Artemis II crew's biological monitoring will help refine the models. The models will not tell you the exposure is safe in an absolute sense. They'll tell you the exposure is within accepted risk thresholds. Those are different things, and it's worth being clear about the distinction. The fourth hazard is the one that feels almost absurd until you look at the numbers. Micrometeorites. The Moon has no atmosphere to burn them up. Every particle of rock and ice and debris drifting through the inner solar system that crosses the Moon's path hits the surface at full interplanetary velocity. The Artemis II crew witnessed at least one impact flash during their flyby, a brief burst of light that mission controllers asked them to describe in more detail. Both Wiesmann and Hansen confirmed seeing it. Neither could say how long it lasted. On the surface, those impacts happen continuously. Most are microscopic. Some are not. A micrometeorite strike on a spacesuit or a surface habitat represents a failure mode that cannot be designed away entirely. The probability of any single strike during a 30-day mission is low. The consequence of a pressurized suit breach in a terrain that is a minimum 250,000 miles from the nearest emergency room is not. None of this is an argument against going. The argument for going is not that the Moon is safe. It never has been. The argument for going is that the scientific return is real. The strategic importance is real. The long-term value of establishing a sustained human presence beyond Earth orbit is real. The ice at the South Pole alone could change the economics of deep space exploration if it's accessible in the quantities the orbital data suggests. The permanently shadowed craters are time capsules, material that has been frozen at -200 degrees Celsius for billions of years, untouched by solar radiation, may contain a record of the early solar system that exists nowhere else in the inner solar system. And the practical case is simple. Every system you need for Mars, life support, radiation management, dust mitigation, long-duration surface operations, all of it can be tested on the Moon in an environment where a rescue mission is at least theoretically possible. On Mars, you are on your own in a way that makes the far-side blackout feel like a brief inconvenience. So the program moves forward. Artemis III, toward the end of 2026, or sometime in 2027, depending on which schedule you believe and how many more delays the program absorbs. A crew will enter lunar orbit for the first time since December 1972. 2 of them will descend to the surface aboard a SpaceX Starship, Lunar Lander, the first humans to walk on the Moon in over half a century. The dust will cling to their suits from the moment they step outside. The radiation will accumulate silently. The micrometeorites will keep falling. The temperature boundaries will wait at the edge of every shadowed region. And somewhere, in a laboratory at Kennedy Space Center, engineers will still be poring over the heat shield from Artemis II, mapping every char pattern, every location where material was lost, running the numbers against the new permeable AVCOAT formulation that will fly on Artemis III, a design that has never been tested at lunar return velocities with humans inside. 2 untested configurations in 2 consecutive crewed missions. That is still the reality, regardless of how the inspection comes out. The moon is not what we thought it was. The Artemis II crew made that clear from 250,000 miles away. Victor Glover said what he was seeing was beyond what human beings had evolved to process. Christina Cook said, "When you have that perspective, you understand everything you need is what Earth provides." Reed Wiseman paused mid-sentence describing Earth from deep space and couldn't find the words to finish it. They came home. The path is open. The hazards are documented, partially mitigated, and in some cases still unsolved. And the people who've been selected to walk on the surface next have read every line of the risk assessments and signed the forms and said yes anyway. That is the thing about exploration that doesn't fit cleanly in a headline. It has never been safe. It was not safe in 1969. It is not safe now. The only thing that changes is how precisely we understand the ways it can go wrong. We're going back anyway, and we should.